are the delay time, rise time, peak time, peak or maximum overshoot, and settling time. So these are the various time response specifications that we will be studying today. So to study this, we are going to consider the time response of a second order underdamped control system subjected to a unit step input. So last class, I had told you to try for the undamped system, isn't it? I told you to derive for undamped system and other systems like overdamped. I don't know how many of you have done that. So today's class, I will just start off with the time response specifications. The time response of a second order underdamped control system subjected to a unit step input. So you can see the screen, the time response specifications. I'll just run that. So consider this. This is for underdamped. So you can see the response for underdamped. You can see the wave which is generated and which is oscillating here. Okay, so here at the origin axis, we have 0.5 and 1. This 1 is called as the final value. We are going to consider this 1, or this is called as 100% of the final value. We have the wave which is generated here and which is oscillating, and this is underdamped. So there is damping here. That means what? The amplitude keeps reducing with respect to the time. So here you can see various parameters which I have written here, like you have rise time, then you have this delay time, then you have peak time, then you have settling time here, and then there is peak overshoot, which is denoted by MP. Okay, then you have this for settling time, we will be considering the allowable tolerance, which can be either 0.02 or 0.05, that is 2% or 5% tolerance. So based on this, we will just refer to this graph. Okay, and I will just start off with the first parameter that you can see here is the delay time. So the definition for the delay time will be what? It is the time required for the response to reach to 50% of the final value at the very first instant. That means what? You can see here the delay time. This is the delay time. So here you can see it is showing at 50% or 0.5. At first instant means what? From origin it is going to start and it is going to end for the 50% of the final value. I said that this 1 is considered to be the final value and 50% of this 1 will be 0.5. So till here you can see that this represents the delay time. Then we have the rise time, PR. It is the time required for the response to rise from 0% to 100% of its final value at the very first instant. So you can see here from 0%. So since this is underdamped system, we have the rise time, which is from 0 to 100% of the final value. Final value is 1. So till here, this will indicate the rise time, which is denoted by small t suffix small r. So for different other damping systems, like for overdamped system, we consider the rise time to be from 10% to 90%. Similarly, for critically damped, we consider the rise time to be from 5% to 95%. And since for our discussion of time response specifications, we have considered the underdamped system, so the rise time will be from 0 to 100% of the final value at the very first instant. That means what? It is starting from the origin. Okay, then we have the peak time. What is peak time? It is the time required for the response to reach the first peak of the overshoot. So here, this is the first peak of the overshoot. So this will indicate the peak time from 0 to this peak value of the first overshoot. This is the first overshoot. This is the second overshoot. This part is the second overshoot. And this is the first overshoot. So the first overshoot, you can see from here to here indicates the peak time. Okay. Then we have maximum peak overshoot, MP. The maximum peak overshoot is the maximum peak value of the response curve measured from unity. So measured from unity means what? This part of the graph. So you can see here from this part, from 1 to this peak value gives the maximum overshoot. And since this is having the highest amplitude, so we call this as maximum overshoot. So these are some of the parameters, and then we have the final parameter, which is settling time TS. As I told you that, okay, for this maximum peak overshoot, what is the formula? This is very important. You have to remember this. If the final steady state value of the response differs from unity, then it is common to use the maximum percent overshoot and is defined by peak overshoot, which is denoted by m suffix p is equal to c of Tp minus c of infinity. That means what? This is C of peak time minus C of infinity means this talks about the final value. So as in the graph I showed you that from 1 it is rising to the maximum peak. So that 1 is indicated as C of infinity. So maximum percent overshoot, always the overshoot or peak overshoot is represented in terms of percentage. So percent MP or percent maximum overshoot is equal to C of Tp minus C of infinity divided by C of infinity into 100. So the amount of maximum percent or maximum overshoot directly indicates the relative stability of the system. So this maximum overshoot indicates the stability of the system. Similarly, we have a settling time or TS. As I told you that any control system which is vibrating should come to rest at certain point of time. So this settling time TS, it is the time required for the response to reach and stay within specified range of its final value. So here we have given two tolerance levels. One is 2% and the other is the 5%. So expression for the rise time. So now, okay, so these are the different parameters that we will be studying, and for each of these parameters we will arrive at the derivations. I mean, we will arrive at the equations by deriving them. So the first one that we are going to study here is expression for rise time. So consider the underdamped system itself. Okay, so you have, this is 0%, this is 100%, which is the final value, which is also equivalent to 1 here, and this is the oscillated wave that is generated. Okay, so now you can see here the response of a second order control system subjected to a unit step input. So in our previous class we have already derived the expression for the second order response, isn't it? So the final derivation that we arrived at was C of t is equal to 1 minus e to the power minus zeta omega n into t divided by square root of 1 minus zeta square sine of omega d t plus theta. So for all the derivations, we should start from this expression of the second order time response. Okay, so label this as equation number 1. So from the figure, you can see that at small t is equal to, since we are talking about the rise time, we will consider t as tr. So for t is equal to tr, so a c of t, that is the response at t is equal to tr is equal to c of tr is equal to, so at tr you can see the value is 1. So this is equal to 1. By substituting for this in equation number 1, what do we get? At the left hand side, you can see for C of t, we have put it as 1, which is equal to 1 minus e to the power minus zeta omega n tr. So wherever you have this small t, you have to replace that by tr, that is the rise time, divided by square root of 1 minus zeta square into sine of omega d tr plus theta. So this implies e to the power minus zeta omega n tr divided by square root of 1 minus zeta square into sine of wd tr plus theta is equal to 0. So since in equation 3 you can see that this tr will always have some definite value. So this term which is associated with tr cannot be equal to 0. So that's why we have taken this term separately and we have written it as e to the power minus zeta omega n tr divided by square root of 1 minus zeta square, which is not equal to 0 because time tr is finite. Since now this part, when this part is not equal to 0, then this part will definitely be equal to 0. So when we equate this to 0, you know that we can write this as omega d dr plus theta is equal to n pi, where n takes the values of 1, 2, 3 and so on. So wd into tr is equal to n pi minus theta for the first time, that is when small n is equal to 1. You keep giving values for the small n as 1, 2, 3, so on. So when n is equal to 1, we get the equation as wd into tr is equal to pi minus theta. Therefore, the rise time Tr is given by Tr is equal to pi minus theta divided by omega suffix d. And we also know what is theta, and we also know what is omega d from the previous classes which we have already studied. So theta is given as tan inverse of square root of 1 minus zeta square divided by zeta. This is from the triangle that we had drawn in the earlier classes. Just go through that. You can find out what is theta. So theta is tan inverse of square root of 1 minus zeta square by zeta, which we have already derived. And omega d is also equal to omega n into square root of 1 minus zeta square. This also we have done it. So by substituting in this equation for theta and omega d, we get the rise time as pi minus tan inverse of square root of 1 minus zeta square divided by zeta, the whole thing divided by omega n into square root of 1 minus zeta square. So remember, these definitions or these formulae for all the parameters which I'm going to derive here are very, very important with respect to the GATE exam as well as with respect to your main university exam, where you will be definitely asked to derive these parameters. And also these final formula you have to remember very well. Okay, so that is the expression for the rise time. Similarly, now we have to start deriving for peak time. So for every derivation, we will consider this underdamped system. Along with that, we are going to consider the time response of second order control system. So now expression for peak time. So here, this is the peak time, isn't it? So this is the peak time. So the output response of a second order is subjected to a unit step input is given by, so this formula you have to remember. So write down that equation from the above figure at time t is equal to tp. Now for rise time we had taken small t as tr. Now for peak time we are going to replace this t by tp. So for this we have one change here. What is that we are going to do here? We are going to differentiate the output response with respect to the time here. So from the above equation at time t is equal to tp, the slope of c of t must be 0. The slope of c of t, this must be 0. So for that, what we are going to do is we have to differentiate this output response c of t with respect to time and equate that to 0. So d of c of t by dt at t is equal to tp is equal to, so the the differentiation of 1, which is a constant, is 0, minus what you can do here is you can apply that u into v, derivation of u, differentiation of u into v, the formula. So u into dv by dt plus v into du by dt. So you have to apply that. So here consider this to be one term and this to be the other term. So this I'm going to now differentiate. So e to the power minus zeta omega n into tp. Wherever you have t, replace that by tp. Very important. Divided by square root of 1 minus zeta square into, so we are differentiating this, right? So you will get this as minus zeta omega n into, write down this term as it is, that is sine of omega d tp plus theta. Then plus, now write this term as it is. See here, I have written down that term as it is and differentiate this sine term. So sine of omega dt plus theta will be what? Differentiation of that will be cos of omega d tp plus theta, and this you still have one more term to be differentiated here since it is associated with t, that is time. So you will get omega d. So we have written that as omega d into cos of omega d tp plus theta, and this is equated to 0. Now further simplification, you can see here what is that they have done. They have taken out minus as common. So when minus is taken out as common, this becomes now plus. So e to the power minus zeta omega n dp divided by square root of 1 minus zeta square into, you can see that we have this minus So this minus we had taken it out. So this becomes a positive term. So plus zeta omega n sine of omega d Tp plus theta minus, because we have taken minus as common. So this plus becomes minus here. So this minus omega n square root of 1 minus zeta square. That is omega d is written as omega n into square root of 1 minus zeta square into cos of omega d Tp plus theta, which is equal to 0. Now you can see, so what is that? In the next step they have done is they have taken out omega n as common and write down the remaining terms as it is and equate that to 0. So now you have cos term and you have sine term. So how that can be written with respect to this triangle here? You can see that this is taken as theta, and but what is cos theta? Cos theta is what? It is adjacent by hypotenuse, isn't it? Adjacent by hypotenuse. So adjacent is zeta divided by hypotenuse is 1. So this will be just zeta, and sine theta is equal to opposite by hypotenuse. So opposite is square root of 1 minus zeta square divided by 1, which is just 1 square root of 1 minus zeta square. Now substitute for this here. By substituting the above equations we get, so this term will be as it is, and for zeta, in place of zeta you can write it as cos theta, and in place of square root of 1 minus zeta square you can write it as sine theta. So when you write that, you will be getting this equation, so which is cos b sine a and sine b cos a. So this can be written as sine of a minus b from your mathematics. So this can be written as e to the power minus zeta omega n into Tp divided by square root of 1 minus zeta square into omega n, and this can be written as sine of what is a? A is omega d Tp plus theta and b is just theta. So it is sine of a minus b. So sine of omega d Tp plus theta minus theta, which is equal to 0, and plus theta and minus theta cancels out. So you are left with the remaining terms e to the power minus zeta omega n Tp by square root of 1 minus zeta square into omega n sine of omega d Tp, which is equal to 0. So this can be written as, when you take this to the right hand side, since you have 0, 0 multiplied with any term will be equal to 0. So we know that e to the power minus zeta omega n Tp is not equal to 0, as I told you, because Tp is finite. Therefore, sine of omega d Tp will be equal to 0, and again further, this implies omega d Tp is equal to n pi, because sine inverse of 0 will be a pi value, and you have to give the values for n as 1, 2, 3. For the first peak overshoot, when n is equal to 1, you will get the equation as omega d Tp is equal to pi, and Tp is equal to pi by omega d, which is equal to pi by omega d can be written as omega n into square root of 1 minus zeta square. To find the time corresponding to first value, so substitute n as, so this is for first value. Similarly, for n is equal to 2, you will get Tp as 2 pi by omega d, which is 2 pi by omega n into square root of 1 minus zeta square. To find the time corresponding to the second undershoot, substitute n is equal to 3 and so on. So this will be your peak time. So Tp is equal to pi by omega d. So this you have to remember, and it is for n, if you start giving values, you will get it as 2 pi by omega n, 3 pi by omega, 2 pi by omega d, 3 pi by omega d, and so on. So this is the expression for peak time. Similarly, we have to now derive for maximum peak overshoot. So for this maximum peak overshoot, I have already told you the equation, which is given as percentage MP is equal to C of Tp minus C of infinity divided by C of infinity. So what we have to do to find out this MP is, first we have to find out C of Tp, then we have to find out C of infinity, and then substitute in that formula. Sorry. Substitute in that formula, and then you can easily derive the equation for MP. So here you can see peak overshoot is the difference between the peak value and the this is the peak value and the final value. The output response of a second order control system subjected to the unit step input is given by, so again write down the expression for the time response of second order control system. Then by substituting P as Tp, I told you, right, you have to first find out C of Tp. So for that you have to replace this T by Tp. We get the peak response or the maximum response as maximum response C of Tp is equal to 1 minus, wherever you have small t, replace that with Tp. Okay, so you will get this equation. Now C of Tp is equal to 1 minus, what is that they have done here, where you have this Tp, we have already found out the expression for Tp, which is pi by omega d. So pi by omega n into square root of 1 minus zeta square divide, we are writing here in this form because we can cancel out these terms. Okay, otherwise we could have just written it as pi by omega d. Since we can simplify this further, we can just expand that omega d here into sine of omega d into Tp. Now there is omega d here, so that's why I have retained this Tp as pi by omega d plus theta. So these terms will now get cancelled, and so finally what is that we are left with? P of Tp is equal to 1 minus e to the power minus zeta pi divided by square root of 1 minus zeta square divided by square root of 1 minus zeta square into sine of pi plus theta. So now sine of pi plus theta is nothing but it is minus sine theta as per the trigonometric equation. So therefore C of Tp is equal to 1 minus e to the power minus zeta pi by square root of 1 minus zeta square divided by, see this you should take care, you should not write the division sign from 1, it is only for this term, this makes a lot of difference, so you have to take care of this. Okay, when you are in a hurry, please don't do that mistake, this entire equation will be wrong and you will not get any marks for this. Okay, so it is e to the power minus zeta pi by square root of 1 minus zeta square divided by square root of 1 minus zeta square into the sine pi plus theta can be written as minus of sine theta. So here you can write it like this, and then what is that we have done now? See here, from this uh, triangle you can find out what is sine theta. So because sine theta is square root of 1 minus zeta square, so you can, these two terms will get cancelled out and you will be left with C of Tp is equal to 1 plus e to the power minus zeta pi divided by square root of 1 minus zeta square. So we know that peak overshoot is given by, as I told you earlier, Np is equal to C of Tp minus C of infinity. Okay, by C of infinity. So there is some mistake here. It should be written as this whole thing divided by C of infinity. So Mp is equal to C of Tp is what? 1 plus e to the power minus zeta pi divided by square root of 1 minus zeta square minus C of infinity. I told you that this is 1. So this is 1 divided by 1. So now 1 and 1 gets cancelled here and we are left with Np as e to the power minus zeta pi divided by square root of 1 minus zeta square. So now percentage peak overshoot is given by this formula. So finally you have the equation as e to the power minus zeta pi divided by square root of 1 minus zeta square into 100. So very important. Okay. So that was for unit step input. Now when you consider an amplitude of A, then you just have to multiply this NP by capital A. So that, and you will be getting the peak overshoot as e to the power minus zeta pi divided by square root of 1 minus zeta square into 100. So this is the final equation. So for unit step input or for any amplitude, it is not dependent on this amplitude term. So your peak overshoot will be just equal to e to the power minus zeta pi divided by square root of 1 minus zeta square into 100. So in the gate problems, just to confuse you, they will ask for unit step and for amplitude, what is the formula? It is the same. So do not get confused here. You have to remember this. Okay, so next expression for settling time. So all these equations, make a list of these equations in one single sheet and every day you just see those equations, you will remember better. Okay, so expression for settling time. So expression for settling time, here we have to consider, as I told you, the tolerance levels, either 2% or 5% tolerance level. So here the output response of a second order system is subjected to a unit step input is given by. So consider from this. Then so here they have considered for 5%. So it is the envelope time response is given by here. You can see here the upper envelope and the lower envelope is considered. Okay, so the upper envelope and lower envelope, and this is the final value, which is 1, with a tolerance level of plus or minus 5% is 1.0. For the upper envelope it is 1.05, and for the lower envelope it is 0.95. So for upper envelope you should write it as 1 plus e to the power minus zeta omega n t divided by square root of 1 minus zeta square, and for the lower envelope it will be just 1 minus this expression of ts. Okay, so just make a note of that. So 1 plus or minus upper bound, and this is lower bound. From the response, the upper bound is given by, so you just write down this expression from the graph, and the lower bound is given by this expression 1 minus e to the power minus zeta omega nt by square root of 1 minus zeta square, which is equal to 0.95. So ideal settling time Ts for 5% tolerance in both the cases, for upper bound as well as the lower bound, we get the expression as e to the power minus zeta omega n into ts. Wherever we have t, replace that by ts divided by square root of 1 minus zeta square, which is equal to 0.05, because it is 5% tolerance. So that is equal to e to the power minus zeta omega n ts, which is equal to 0.05 into square root of 1 minus zeta square. So now take the natural log on both the sides. So natural log on both the sides we have to write down like this. So this equation you have to remember, I mean the natural log, you have certain rules. So natural log of x to the power y is given by y into natural logarithm of x. Similarly, natural logarithm of x into y is given as natural logarithm of x plus natural logarithm of y. So therefore, now apply this in this equation. So you will be getting it as minus zeta omega n ts natural logarithm of e, which is equal to natural logarithm of 0.05 plus natural logarithm of square root of 1 minus zeta square. So minus zeta omega n ts is equal to natural logarithm of 0.05 plus natural logarithm of square root of 1 minus zeta square, because natural log of e is equal to 1. So therefore ts is what? It is minus 1 over zeta omega n into, find out the natural logarithm of this, you will get it as minus 2.99 plus natural logarithm of square root of 1 minus zeta square. So ts is equal to minus 1 by zeta omega n into minus 2.99, because natural logarithm of this will be very, very small, which can be neglected here. Therefore, for approximate 5% settling time, Ts is equal to 3 divided by zeta omega n. Similarly, for 2% settling time, you have to find out in the similar fashion. So you will get Ts as 4 by zeta omega n. So this you have to remember. Okay, for 5% settling time and for 2% settling time, what is the expression for Ts? You have to remember. So this is about the various time response parameters that we are going to study to get the desired performance of the control system. Now coming to the steady state errors and error constants. So this is again a very, very important topic. But before that, I will just give you a glimpse of what is meant by this. See, when we have to study about the steady state errors and error constant, you have to know the types, like type 0, type 1, type 2. So how based on how do you call this is a type 0 system or this is a type 1 system? For that, you have to see the number of poles which are present at the origin. If the number of poles present at the origin is 0, that means if there are no poles at the origin, then we call that as type 0 system. If number of poles which are present at the origin is 1, then we call that as type 1 system. Similarly, if the number of poles are 2, then we call that as type 2 system. So how do you decide whether how many number of poles are present at the origin? Suppose closed loop function is given by a polynomial. So it will have polynomial means it will have both the numerator polynomial as well as the denominator polynomial. So the numerator polynomial are responsible to find out the zeros of the system, and denominator polynomials are responsible to find out the poles of the system. And in the denominator, you have to importantly see whether there is a single s present. If there is a single s present in the denominator polynomial, you have to see the power of that s. If the power of the s is 1, then we say that it has a single pole at the origin. If the power of s is 2, then we say that there are two poles at the origin. If the power of s is 0, which is as good as saying that there is no s term in the denominator polynomial, then we say that there is no pole which is present at the origin, and we call that as type 0 system. So this is how you decide about type 0, type 1 and type 2 systems. So now let's study about the steady state errors and error constants. So here if you consider a closed loop. Okay. Now why okay. Study what is meant by this steady state error? The steady state errors and error constants are very important in gate questions. Okay, so this is a very important topic to answer the gate questions. Most of the questions will come from this part of the control systems, because you have many number of problems in this. So what is meant by the steady state error? So steady state error is the value of error signal when t tends to infinity. The steady state error is the measure of system accuracy. This also we have discussed earlier. These errors arise from the nature of inputs, type of system, as we have discussed just now, what is type 0, type 1, type 2. So these errors arise from what? From the nature of inputs. Nature of inputs means what? Whether it is a step input, ramp input, parabolic input or impulse input, signal inputs which we are giving to the system to excite the system. So it depends on the nature of inputs, it depends on the type of inputs, and also it depends on the non-linearity of the system components. So linearity and non-linearity, here it depends on the non-linearity of the system components. So now you see here, consider a closed loop system as shown in the figure below. So you are considering a closed loop system here. This has input, reference input R of S. Then you have this open loop forward gain, which is given by G of S. Then this is the output, which is the C of S. This is the desired output. Sorry, desired output is this, and this is the actual output. Then you have the feedback parameter, which is feedback signal, which is denoted as H of S, and then you have this negative feedback given here. This is the negative feedback, and this B of S is nothing but H of S and into the part of this. This is C of S. So B of S will be H of S into C of S, and this error signal is the difference between this input and this feedback input, which is called as the error signal. So steady state error is the difference between the actual output and the desired output. In the time domain, the steady state error is the value of the error signal as t tends to infinity. Therefore, steady state error SSE is equal to limit as t tending to infinity E of t. This is in time domain. Using final value theorem, equation 1 can be written as limit of E of t, where t tends to infinity, is equal to, in S domain you can write this as limit as S tending to 0, S into E of S. This is also very important from the final value theorem. So therefore, SSE is equal to, in time domain it is t tending to infinity, and in S domain it is S tending to 0. Any problem? Okay, so from the block diagram of this error signal, you can write E of S as the difference of R of S minus B of S, where E of S is the error signal, R of S is the input signal, and B of S is the feedback signal. So from the definition of transfer function, we know that h of s is what? B of s by C of s, because this is output by input. So output of h of s will be B of s and input to h of s is C of s. Or what is B of s? B of s is C of s into h of s, which I just now told you from the figure. So substituting for B of s in 3, you will get E of s as R of s minus C of s into h of s. From this figure, you can find out what is C of s. It is, from the figure C of s, you know it is E of s into G of s. So substituting for all these parameters, finally you have to find out the error signal E of s, which is given by R of s divided by 1 plus G of s into h of s. So if the system is unity feedback, then h of s will be 1, which gives E of s as R of s by 1 plus G of s. Therefore, error transfer function is given by E of s by R of s equal to 1 by 1 plus G of s into h of s. So steady state error is given by limit as s tending to 0 s into E of s. So substitute for that, you will get steady state error as limit s tending to 0 s into R of s by 1 plus G of s into h of s. So this is about the steady state error, and in the next class we will study about the error constants. So in this error constants, you have to study two types. One is the static error constant and one more is the dynamic error constant. So first we will consider the static error constants, and in that we have again position error constant, velocity error constant, and acceleration error constants. So this Kp will be given by limit as s tending to 0 s into E of s. For Kv it is s square into E of s. Similarly for Ka, you have to see what is that. So in the next class we will study about the different types of static error constants and how to get those static error constants, and also we have to discuss about some problems related to these steady state error and error constants. Okay.